Hi everyone. So in this demo we'll be doing what's called a model validation laboratory, which is very common in introductory control courses. So that is when you, for example, for DC motor, you can model it using a simple first order transfer function, and that's what we'll be showing today. Um, in this version we'll just be using, as detailed in the PowerPoint presentation, we'll be using a Simulink diagram / core controller that is already supplied with the Qube Servo curriculum. And this is a good time to also show that it does in fact come with, for example, instructor and student workbooks, all A-bit aligned, and it shows you the entire process, how to run different controllers, and has you know many has all the laboratories in here. Solutions, a bit of background, and all that stuff. So that is one thing that is also nice to show. Okay, so let's get to the demo. I have MATLAB already open, so make sure you have, if you go to the Fundamental Control Labs inside the Qube Servo 2 DVD, go to DC Motor, and then there's a folder called Bump Test Modeling and Controllers. So in here you'll find the controllers that are supplied for this particular lab, which is called Bump Test, and we'll be opening up Qube 2 Bump Test Validation MDL. So open that up. Here's the Simulink model. Now Bump Test is basically it's a name given for a step response type modeling, right? So we give a step response to the motor, as well as the transfer function here that I was talking about, the first order transfer function. And those are both plotted on the same scope. So we plot the speed of the Qube Servo 2, as well as the simulated transfer function based response, all in the same scope. And this will run for 2.5 seconds. Note here that the transfer function here is basically, it's taking the derivative, that's why there's an S in the numerator, but it also has a low-pass filter. So you can think of this as a derivative and filtering to make sure there's not too much noise in the output. Go to Quark and build. It's already set up to be, it's already configured to run, to generate Quark code. And then we can go to Quark and start. And this will run for 2.5 seconds. Okay, so if we look at the, so as you can see, the voltage goes from 0 to 2 volts at the 1 second mark. And the controller runs for 2.5 seconds. You could, of course, change this. If we look at the speed, you'll notice that, so the yellow is the measured speed from the servo, while the purple line is the simulation from the first order transfer function. These are not matching right now because the model parameters are incorrect. These are just default model parameters. So through the bump test lab, the student would find the steady state gain, the DC gain here, K, as well as a time constant, tau. So right now we're using 10 and 0.1. Now we can, of course, change this. For example, if I use 25, and then I'll keep the time constant the same. Then we can start. Okay, that's a bit better. So now my simulation actually is a little bit larger than here, my DC gain. So I need a bit less. So maybe 23. And then I can see as well as the delay, right? So the simulation is responding too quickly. It should be slower to match the yellow measured response. So in that case, I can add a small delay of 2. So 0.12 instead of 0.1, which will make it a bit more slow. Okay, there we go. That's a bit better. So let's modify this a bit more delay in the model. Okay, that's not too bad. How about 0.17? There. So that more or less you get, you could also call this like model matching. what I've shown in this demo is basically doing it on the fly, right? So you would derive these, of course, from the bump test response, or you could derive it another way. There's different labs, different ways to do it in the curriculum supplied. But this is one method, an experimental method. For example, if you think of this in an industrial sense, if you had a system like this where the parameters do not be known, also known as like a black box type system, then you could do this experimental type of modeling to find out what the dynamics are of that system.